either there's a common reactant or a common product. Like the common reactant would be both an oxidizer and a reducer, or the common product would be both an oxidizer and a reducer. That's a disproportionation reaction. Do you have the reaction?
Yeah, it's
Or just
AS2 AS2S3 plus H2O2 goes to ASO4 3 minus plus SO2 or SO4 minus.
all right. So something like this. The first thing I see is hydrogen peroxide. Hydrogen peroxide is a good oxidizer, although it could go both ways. It could be an oxidizer or it could be a reducer. And then this. When I look at this, arsenic is going to be in the 3+. The max oxidation state for arsenic is 5. This is right below phosphorus. And so arsenic could be oxidized, but compared to sulfur, sulfide's going to just be much easier to oxidize. And in fact, sulfides in general are easy to oxidize. And so this is why I told you about, I used to work with thiols. Did I tell you that? And everything would smell really bad, like skunk odor. And so it just bleach it out. Bleach it out because most thiols are like, they have S in the 2- state. It's easy to oxidize. You oxidize it completely to sulfate. Sulfates don't smell. And so what I do at the end of the experiment is just bleach everything out. But I could have used hydrogen peroxide as well. When we look at this, though, we definitely oxidize sulfide. We went from -2 to, what's this over here? +6. And so we definitely oxidize sulfide. But what happened to arsenic? So if we look at arsenic, this is -2. Arsenic would be what?
+5.
Yeah, +5 here. And then over here, arsenic is +3. So actually, hydrogen peroxide was able to oxidize both the sulfide and the arsenic in this particular reaction. Why they call it disproportionation reaction, I don't know. This one's a bit odd because we're just oxidizing both, and they form different products. And the usual disproportionation reaction, the same species would be both the oxidizer and the reducer. Well, this is the reducer. It's just 2 atoms got lost electrons. Reducing agents lose electrons. The oxidizer. And so technically, I wouldn't call this a disproportionation reaction. Was that the question? Why is this a disproportionation reaction? I know the question was about basic solution, but it has nothing to do with acidic or basic conditions at all. So it just has everything to do with the species itself here. In fact, we're going to look at a disproportionation reaction today. And so,
and then the answer was like a basic solution. They did the thing with the...
Yeah, converting it from acidic conditions to basic conditions.
But they don't clarify that it's in a basic solution.
Oh, they didn't say it was in a basic solution? If they didn't say it was in a basic solution, then you stop with acidic. They would have to specifically tell you it's in basic solution. You can do this easily by just adjusting the pH by adding acid or adding base. Sometimes when you add acid, it really speeds up the reaction, so we often do that. Or sometimes when you add base, it speeds up the reaction.
I have another question.
Okay.
70C, it was nitrogen gas, or preparation of nitrogen gas
Okay.
by mixing liquid bromine and ammonia in a solution. And then they said the products that were given were nitrogen gas and
so they mix bromine with ammonia. Bromine we know is an oxidizer. Ammonia is a reducer. Ammonia is electron rich. Nitrogen's in the -3. So we expect some redox reaction here. So if bromine takes electrons, it can't take any electrons from hydrogen, it's already +1. So we'll take it from the nitrogen, and if we can oxidize it completely, to the element here. This is not complete oxidation because nitrogen can go all the way to what? The other way, the other direction, +5. So nitrogen can go all the way to +5. So we're doing partial oxidation. We want to stop at N2. And so sometimes that means adjusting the conditions so that we stop at N2 rather than going. For example, this one you can see it didn't stop at sulfur, elemental sulfur. This one got, pretty much blasted all the way to sulfate. So this was complete oxidation. Not only complete oxidation of the sulfur, but complete oxidation of the arsenic. And so that depends on the conditions. So if you have mildly oxidizing conditions, that is, mildly could be use a weaker oxidizing agent. That's one. Or alternatively, do you know an alternate way of making it mild? An alternate way of making it mild is to reduce the concentration. The chart, do you know what the concentrations on the chart are? We're using what are called standard thermodynamic conditions. Standard thermodynamic conditions have a fixed or set concentration. That concentration is 1 molar. Good. And so this is partial. Bromine's not oxidizing it all the way. And so it's just partial. And that depends on the conditions. Maybe bromine's not strong enough. And so this is the advantage of skeleton. You just try it and see what happens. This is what you form. Sorry, what was the question about this?
I was having trouble with balancing the reaction, especially because ammonia goes to...
Yeah, this would be more of a disproportionation style in a way, because ammonia goes to two different things. And so how do you deal with something like this? We just have to follow the atoms. And so that means, although this is, in a way, it's kind of different. This is all they gave you?
Yeah.
Okay, so we know that bromine is going to go to ammonium bromide. Did they say ammonium bromide aqueous or just ammonium bromide? Solid.
They didn't clarify.
They didn't clarify. Okay, so I'm going to...
It was in an aqueous solution.
Okay, then ammonium... So there are different things we could do for this particular one. If it's in an aqueous solution, the different things that we could do is we could do nitrogen gas like this, plus ammonium bromide, strong electrolyte, weak electrolyte, or non-electrolyte? Strong. So this would go to ammonium and bromide. And so this would make it a little easier to split. So here, what I'm going to do is I'm not going to do it like this. I'm just going to say that bromine goes to bromide part. That's one. And the other one is going to be this. It's going to be NH3 goes to N2 plus NH4 plus. Is that what you did?
Yeah, maybe I did it wrong. I got more bromides than ammonium ions, and so it wasn't...
Oh, it didn't... Okay, let's take a look then, what we get. So this one we can copy off the chart. Bromine plus 2 electrons goes to 2 bromides. This one we'll have to balance. But the weird thing is the nitrogens aren't balanced here. So over here I have how many nitrogens? 3. So I'll need 3 here. And then I look at the hydrogens. 3 times 3 is 9. This is 4. So I'm going to add 5 H pluses. And then I look at the oxygen. Actually, there are no oxygens. Oxygen, then hydrogen, sorry. And then what else? Electrons. So 0 plus 5 plus 6 means 6 electrons over here. Is that what you got? And then we'll just add them together. This first one I'm going to multiply by 3 and then combine it. And So I'm going to have 3 bromines plus 6 electrons plus 3 ammonia. This is going to produce N2 plus NH4 plus 5H plus 6 electrons. 6 electrons cancel.
You're missing the bromide ions.
Oh yeah, how many bromides? Plus 3, 6 bromides. 6 bromides. Okay, so the 6 electrons cancel, and then, so you're saying there's a mismatch between the ammoniums and the bromide. Well, you have to remember this. When we do chart method, we always end up with the net ionic equation. If we end up with a net ionic equation, that means any spectators were already canceled out. And so what you have to do is you have to just make sure the charge balance and the atoms balance. And so we have 6 bromines here, 6 bromines here, 3 nitrogens here, 2 plus 1 is 3 nitrogens, and then 9 hydrogens, so that's 4 plus 5 is 9 hydrogens. And then we check the charge. This is neutral, 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 plus 1, plus 6, minus 6. So the charge is balanced. Now, we end up with a net ionic equation that's going to look like this. Let's see if I can pen that's not all dried out. And so the net ionic equation is going to be 3 bromines plus 3 ammonia yields nitrogen plus ammonium plus 5H plus 6 bromide. And so, actually in this particular case, what we could do is we pair it up like this. This is how it would be paired up. So 1 ammonium will combine with 1 of these, and so that will make 1 ammonium bromide here. And then the remaining 5 H pluses will pair up here, and so that will make 5 HBRs here. And so the CE for this particular equation, we have to work backwards. Sometimes it's more difficult because the spectators canceled. In this case, it didn't. And so we end up, if we want the CE, we end up with this, N2 plus 1 ammonium bromide plus 5 HBRs. Do you see that, how that works? Okay, and so that's what. Sometimes on other ones, like when we're dealing with nitric acid, you know, when we're dealing with nitric acid, the half reaction for nitric acid is like this. It's going to be nitrate plus 4H plus 3 electrons yields NO plus H2O. Actually, how many? 2 H2Os. This one's a little weird because only 2 of the oxygens. Normally if I have 3 oxygens, I need 6 hydrogens. But in this case, 1 of the oxygens stays behind and only 2 of the oxygens leave. So since only 2 of the oxygens leave, 2 of the H pluses. So you might notice here there's a mismatch. Do you see that? Let's say if this were nitric acid, you know, if I get this 4 nitric acids, because I need 4 H pluses, so I need 4 nitric acids. What happened to the other nitrates? I only have 1 nitrate here out of the 4. So what happened to the other 3 nitrates? The other 3 nitrates are spectators, it turns out. And so I'm going to have 3 nitrates that are going to be, if I use nitric acid. The other option is if I use nitrate salt and acid. If I use nitrate salt and acid as a mixture, I can mix them in any proportion. But if I use nitric acid, then they're going to be in 1-to-1 ratio. Here I should have 4-to-4, but I don't. And so what happens here is that 3 of the nitrates don't participate, and they get eliminated. So this would be the ionic equation for this. And then if we go to the CE, the conventional equation, it would um, it would have to balance out there. Does that make sense? So sometimes, so when we do this, we just end up with a net ionic equation, and then we have to work backwards to get the complete equation from there. I've asked that, I've asked that on exams before to tell me what the complete equation is. This is not in Chem 1A. In Chem 1B I've asked this. Tell me what the complete equation is. And it is working backwards, but I never really did that. Maybe I didn't do any examples of that in class. I just wanted to see if anybody could figure it out. But in the class, maybe only 1 or 2 people figured it out to go backwards and then figure out what the complete equation was. But most people, they just got really tripped up on it. I just asked that, I think just once in the past. It's not common. We just leave it at the net ionic equation. But if you're going to buy chemicals, then it's common. If you're working in the laboratory, then you got to buy the chemicals. We got to figure out how much we need to get. And so there it would be more common in actual practice. Okay, any other questions? No other questions? Okay. I understand, things about regarding parking and everything else. But just be aware that there are some instructors here, because they cover safety at the beginning of class. If you miss the safety, then they bar you from lab that day. And so a lot of instructors here, they don't like. I try to wait because it was empty today, so I try to wait before talking about the lab. But you should try to get in. But is there something going on? There's still a lot of people missing.
There's heavy construction on Crenshaw.
On Crenshaw?
Crenshaw's
Okay.
down to one lane.
The student lot over there was like,
Oh yeah, Lot L is like half full of like big old trailers and stuff.
Oh,
And then
right.
Crenshaw's down to one lane.
Okay, that's it. I'll just record this. Yeah, KCl3 is not the happiest, most stable chemical around because of the +5 oxidation state on chlorine. That +5, is that the max on chlorine? No, it's not the max, but it's high. And so with this stuff, you really want to be careful with this. So what this means is that if I ever heat this stuff up, I would do it probably with an explosion shield just to make sure, it doesn't explode. Like ammonium nitrate. You guys remember ammonium nitrate? Did I talk about ammonium nitrate? Ammonium nitrate you don't want to heat up because it'll explode.
Is that tannerite?
Yeah, no, tannerite I think is like, what is it, nitroglycerin and sawdust or something like that?
I thought it had a...
Did it have ammonium nitrate in there too? Yeah, sorry, I don't know. No, there was one guy who knew all that stuff. Student. Let me see. Ingredients. Yeah, actually, wow. Tannerite. Tannerite's even nastier because tannerite has not just ammonium nitrate, but it also has this ammonium. What's that called? No. ammonium perchlorate, and aluminum metal. Yeah, this is a very dangerous mixture. Why is that? Let's see how much. Okay, one, ammonium nitrate and ammonium perchlorate are very dangerous, much more dangerous than potassium chlorate. Much more dangerous than potassium chlorate. Because when I think about chlorate, you know, potassium ions, are they very reactive? No. Potassium ions, not reactive at all. Chlorate, I would think of as a pretty good oxidizer, a pretty good reducer. Is it electron rich or electron poor? Oxidizers are electron poor, so reducers are electron rich. So. Well, ammonium perchlorate, I talked about perchlorates in the water, drinking water in Nevada. Did I talk about that?
Yeah.
Very difficult to remove because perchlorates are all soluble. So,
We just need to find a reaction to
yeah, it's not so easy.
yeah, that would be
do. But the perchlorates were from Pepcon. Have you heard of Pepcon?
No, I don't think I have.
Let's see. Maybe this is.
It sounds like an off-brand joke. That's fine. Oh, nice. This reminds me of a documentary on the Devil's Lighter, which is a not gas explosion, but a gas release at a oil plant that had a spark that lit it on fire, and for I think like several days, the flames just shot into the sky, illuminating the area. No one was allowed near it, but it was a very, very cool sight.
See if I have. Yes, sorry. Find the right video.
That'd be an odd
I don't know if we have audio. This is a big fire for.
Ooh, that's gonna be loud.
I think you could hear through the audio. Yeah, you can definitely.
pretty far away. That's why. I actually haven't seen this one. We'll just watch the audio reconstruction. This is a factory there. Fire. Most people were evacuated, but not everybody. So unfortunately, there's some deaths. The factory. Slow this down. This is really good.
You know what I find so interesting about this footage, Professor?
What?
When you see the fire go up, you can see three different colors.
Oh,
The
yeah.
light grays, the dark, what is it? The dark blacks, and the bits of yellow and orange.
Yeah, There's a lot of mixture of products in there. This is like skeleton redox. You just do it and see what happens, and then try to analyze that,
I'm not sure.
and
how
then
well
see
that
what you
would,
actually
factory.
formed. Because yeah, you gotta believe there's a lot of different products in that. It's not such a simple redox reaction there.
Do you think all of the explosions that happened at that factory were related to what was inside the factory?
Yeah.
Or do you
Well, I don't know recently, but this one, yeah. So let's see. Just catch this, the last one.
the biggest
Oh, that's no wonder I was looking at the not the I was looking at the hours. I thought this was just a few minutes long, but you kind of fast forward there. All right, I think around 6 minutes.
Yeah, you get these small ones. The big explosion just really makes it a nice one for the club.
Yeah.
Me like
Okay, those are the two little ones. Okay, let me fast forward this. It's about around here. So did you figure it out? Ammonium perchlorate. Give your time. Give some time for your mind to think about it. Why is ammonium perchlorate much worse than potassium chlorate?
Bigger explosion.
No, you could have a big explosion with potassium chlorate too.
I'm assuming that after it reacts, it's very toxic in the air.
It has something. It has something to do with the inherent properties of ammonium perchlorate versus potassium chlorate.
The oxidation states of the chlorine.
Well, one, the oxidation state of the chlorine. Yeah, that's one of the things. In ammonium perchlorate, the oxidation state is +7, which means it's even more of a what? I asked you this, is this an oxidizer or is this a reducer? Potassium chlorate, when you look at potassium chlorate, you think nothing of potassium. This is the chlorate. What do you think of potassium chlorate? What is it? Oxidizer or reducer? Well, you still don't have the terms. The terms have got to come quickly. And this is why you want to do the repetition. You want to do the repetition so that the term, this is preparation for the next test, which is next week. But they're coming too slowly right now. They got to come faster because you have to have them down. This is what I mean by having the basics down. You have the basics down through drills and memorization, that kind of stuff, so you can do the more challenging stuff. It's like practice, practicing. If you're practicing for a big, sports event, you want to have all the basic drills down, right? So that during the event you can do whatever you can do. But this is it, the terminologies: oxidizer, reducer, reducing agent, oxidizing agent, oxidation, reduction. All those are confusing, and so you don't want to wait until the night before the test, or just before. And so, is that electron rich or electron poor? Would you say potassium chlorate?
I'd say it would be a
Yeah.
That is an oxidizer.
It's an oxidizer. But tell me about ammonium perchlorate. It does have acid base. There are acid base properties, but acid base properties are negligible. I mean, yes, there are acid base. Ammonium's an acid, but it's so weak. And perchlorate is so weak that we call it neutral. It's not even basic, and so it's ammonium. So this ammonium perchlorate is a weak acid, Bronsted. And so, what's that? Lewis? It could react Lewis for sure. It could be some Lewis, but really what stands out are its redox properties. Would you label ammonium perchlorate as strong oxidizer?
Yes.
But it's kind of a weird one. How would you label it?
I would label it as an oxidizing agent.
As an oxidizing agent?
It's still oxidized.
Oh, so it's an oxidizer just like this,
Yes.
but a little stronger.
Yes.
That's how you'd label it?
Yes.
Okay. And so ammonium perchlorate is electron poor because it's got chlorine in the +7. But what about, oxygen and hydrogen are happy. Hydrogen is a +1, oxygen is a -2. Those are happy as is. But what about nitrogen? What is nitrogen?
Nitrogen is at -4.
Not -4.
-4.
Ammonium's +1. It's -3. What do you think about nitrogen in the -3 oxidation state?
I would imagine it to be unhappy because it can go from -3 to +5. It's not where it wants to be. It's not entirely unhappy, but it's not where it wants to be.
Yeah. And so it turns out that this is electron rich. This is electron poor. Electron poor is what we call a reducer or reducing agent. Electron poor is not a reducer or reducing agent. Electron poor is a oxidizing agent or oxidizer. Electron rich is
The reducing agent.
reducing agent. This is very dangerous. Why is this very dangerous? Because
It's already a reaction in itself.
yeah, you have the two reactants in the same compound. And so you just got to make sure that they don't get hot enough to react. Unfortunately, they got hot enough to react there because the ammonium and the chlorate, they're locked in their lattice position. As long as they stay in their lattice position, they're all right. But if they start to vibrate too much, and then there's because the vibrations also follow that curve. Remember that curve? What's that curve called? Maxwell-Boltzmann distribution of thermal energies. And so there's can be some more extreme vibrations. If there's extreme vibrations, what's going to happen? They're going to collide and they're going to react, and then you're going to have big trouble. This is big trouble here. Ammonium perchlorate's big trouble.
It's a reaction.
This is why ammonium nitrate's the same thing. Nitrate is electron poor, and ammonium is electron rich. Everybody thinks nitrate's electron rich because it has a negative charge, but we don't look at that negative charge because the negative charge belongs to oxygen.
We look at the oxidation.
Yeah, we look at the oxidation states, not the net charge when we're analyzing this. And a lot of people think ammonium is electron poor because it has a positive charge, but it's not. That positive is on hydrogen, not on nitrogen. And hydrogen's happy with a positive charge, it's no problem. Oxygen's happy with a -2, that's where that minus comes from. There's an extra electron to make oxygen happy. And so ammonium nitrate, there have been a lot of accidents. Pepcon was one. Did you hear about the chocolate factory explosion that killed 6 people, I think? Over the weekend? When did that happen? Saturday?
I have not heard of any chocolate factories.
You didn't hear about the chocolate factory explosion?
No, the
I
only.
don't think so.
I'm sorry, the only chocolate factory I can think of right now is Willy Wonka. It's because I watched.
It wasn't the Wonka factory though.
I just watched the movie recently. I'm sorry.
7. 7 people dead.
It was a huge explosion.
Chocolate.
Chocolate's a fucking universal sugar.
But do you think chocolate is electron rich or electron poor?
I would say it's pretty stable. I would say electron poor if anything.
How can you tell?
Maybe
You know my.
slightly rich because you eat it.
Does it have any calories? If it has no calories, then chocolate is neither. You know, if something has calories, then that means it's a fuel and we can burn it. And what makes the best fuels? Electron rich or electron poor substances? So can you burn chocolate?
Yeah.
You can burn it.
Yeah, you can burn chocolate. You know, this is 4 hours ago. Bodies of all 7 victims of Pennsylvania chocolate factory explosion have been found. Powerful explosion in eastern Pennsylvania.
You know, I think chocolate would be electron.
I'm just curious how, because chocolate, what you try to do is you try to keep the reducers and the oxidizers separate. You try to keep them separate so that they're, yeah, they don't react and you don't have to worry. You know, and if you keep them separate, you'll be okay. But it'll be interesting to see what the reaction was that caused this explosion.
They must have been making a special kind of chocolate for that kind of
I mean,
explosive
yeah, it could have
flavor.
been extra rich. Something.
Maybe there was no sugar in the air.
Sometimes, you know, if you don't know, then you think this. My friend, had applied for a job at Hyperion. During the interview, he was asked one question, and he was asked the question. He was a student that was working with me at UCSB, undergraduate. I was a graduate student, but he asked me this question about. Well, they asked him the question: is sewage sludge a reducer or an oxidizer? And he said he couldn't answer the question. And I thought, wow, that's an easy. For me, that was an easy question. But he said he told me, I bet you couldn't have answered it as well. But I thought, then maybe I don't know who had taught him about this. But to me, it was easy because can you burn sewage sludge?
No.
Well, you know
We can't.
I don't. I don't. Maybe it's experience, but they make these cow pellets and other things for manure. Have you heard of those?
No.
For fires and stuff. Yeah. So you can buy that stuff and you can burn it. That kind of. And then I was thinking, what do? They burn sludge. You see it like in Iraq. A lot of military people are complaining because of the burned sewage sludge is causing them cancer from all the emissions. When you burn it, what are you generating? If it burned cleanly, you'd burn it all the way to CO2, but maybe it wasn't burning so clean, and then maybe they were throwing other stuff in the sludge. All kinds of stuff.
Like the bombings in Iraq, they cause all the sludge.
I'm sorry?
The bombings of Iraq, they cause all that sludge.
No, not. It's from the sewage. What do they do with the sewage? You could do, human waste. What can you do with the human waste? You could bury it, but you could use it as fertilizer. Outhouses outhouses were overfilling, so what they're doing is they're burning it, But it's like in other places, they just dump it into the rivers. Like I was looking at, like in India, places like that. I was thinking. But yeah, so you start thinking, fuels, electron rich, oxidizers, electron poor. Will it burn? That's one of the things. Chocolate, or can you eat it? If you can eat it, that kind of thing. Yeah. So chocolate, I would expect to be reducing agent, but I was thinking maybe it could have been a sugar explosion. What I was thinking is probably a sugar explosion. So then I was thinking, I just talked about that on redox, sugar. So there have been lots of sugar explosions in which people have died. This Pepcon disaster and this one, it hasn't been the worst. You know what the worst industrial accident in the U.S. was? Texas City. Texas City, 600 people died in Texas City. It was ammonium nitrate explosion. This one. But as far as industrial accidents, like in India, have you heard of Bhopal? Bhopal, there was a gas release, a poisonous gas release. It wasn't an explosion or anything, but thousands of people died from that.
I read Mumbai, but not Bhopal.
Bhopal, India. No, okay. Oh, wow. Bhopal is, that was one of the worst chemical disasters. Happened in 1984. And so so I was thinking, you know, when my friend had told me that, then I was thinking, you know, I'm going to try to teach more chemistry. Before I used to focus on physics, you know, because a lot of physics and chemistry, so the emphasis, and that's the way I was taught. The emphasis was on physics, not on chemistry when I was taking chem. And I did very little chemical reactions. And so I was thinking, you know, it's a chemistry. I had one Russian student. Her father was a professor of chemistry in Russia. And then she complained to me, you know, your class is all physics. Where's, you know, there's not enough chemistry. And so I was thinking, she's right. My class was all physics. I was much more math.
Wow, 1984.
This is considered the world's worst industrial accident. And so you should know this. The worst industrial accident in the U.S. was Texas City explosion, ammonium nitrate. This one was horrendous. Union Carbide pesticide plant.
Yeah, over 500,000 people were exposed.
Highly toxic methyl isocyanate. Death toll was over 2,000 people died. Oh, actually, no, 3,000. 3,787 people died.
Yeah, 2,300 was immediate.
Oh, immediate death, okay.
2,787.
Oh, wait a minute, 8,000 died
Yeah, within 2 weeks.
within 2 weeks. This was a horrendous accident. So at least for these kind of explosions, we should know, you know, what to mix.
What went wrong, how we can.
Yeah, right, to try to avoid these accidents in the future. I mean, they keep happening, these accidents keep happening. Accidental release, you know, accidental release of radiation, accidental release of super toxic gases, accidental release of many things, very common accidents, and then explosions are other common accidents that happen, so try to be aware of these types of things.
We keep finding new ways to apply chemistry in our everyday life.
Yeah, but it keeps happening, you know, it doesn't, like these sugar explosions keep happening. Almost every year I read about sugar explosion or grain explosion. But anyway, so it's good to know some things like, you know, I don't treat ammonium perchlorate the same as I treat potassium chlorate. Potassium chlorate, yeah, that's a powerful oxidizer. So when I melted it, I said, you know, I used to throw in little combustibles in there and you have a little mini explosion or fire, right? And then I talked about the gummy bears. Did I talk about that? Yeah. That's fine as long as you don't put the reducer with the oxidizer. You know, it's somewhat safe. But here, when you have the reducer and the oxidizer in the same compound, that's a whole different level, right? These are very dangerous. But nonetheless, we're working with potassium chlorate, so as long as we don't have reducer in there, it's okay. But if you get it very hot, I would start to worry. If you get this very hot, then chlorine, you know, is going to be much more reactive, you know, because it's got a lot more energy, kinetic energy at least. And so, you know, if there's a violent collision here, well, what's going to happen? You got chlorate, you know, chlorate ions. What are the three types of motion?
Rotational.
Translational and vibrational. So if this thing is vibrating, the chlorate ion, what can happen? Well, the chlorine can start to look at the oxygen and go, And if the chlorine got enough strength, right now chlorine's not strong enough to take it from the oxygen, right? But if you start heating this up, then the chlorine might have enough strength, at the tail end of the Maxwell-Boltzmann distribution to actually take an electron from oxygen. And actually, that's what we're doing today. We're going to give this some heat, and then we're going to have chlorine take electrons from oxygen. But somebody's already done this before, and since oxygen does not want to lose it, it's not a violent reaction. It's a little bit violent, but not explosive violent. And so if you were doing this on your own, you would do this with all kinds of protection, because you wouldn't be sure if it could explode or not explode, right? And so we would do this. And so this is, somewhat stable, but if you heat it up, then that changes everything. And then what happens is the chlorine is actually going to oxidize all the oxygens. And what we're going to be left with is KCl and O2 gas. And then we'll balance this. For every KClO3, we'll have 1.5 moles of O2 gas form. And so this will be solid. So, oxygen's happy as is. It doesn't really want to lose its electrons. So we have to force this. And not only are we going to force this with temperature, we have to add a catalyst to this. Now the catalyst is going to help this process because, it's really hard to oxidize oxygen at a -2. It's very happy at -2. It's like trying to burn water. Is it easy to burn water? That is, water can be considered electron rich if you think about the oxygens being -2, right? But is it easy to burn water, strip the electrons off oxygen in water? No. And so it would be great. Well, it wouldn't be great because then we wouldn't, life on Earth. The first chapter of biochemistry is water. Water is, critical for life on Earth. We wouldn't have life. If you could burn water, then it wouldn't be good. And so what we're going to do is we're going to add a little bit of catalyst. The catalyst, this provides kind of a Lewis acid-based kind of alternate reaction pathway for this reaction to occur. And I have 0 spatulas. So we're going to just take a little scoop. We don't have to, do we have to weigh this? No, we don't have to weigh this. We have to weigh the sample. I think we're going to weigh everything, though. I think we're going to weigh the sample and then weigh the sample plus this. Just find out how much we added. Okay. But we're going to add just a little scoop of this, manganese dioxide, or MnO2, or manganese 4 oxide. And this is going to speed it up. And then we're going to mix it up, and then what we're going to do is we're going to heat it here with this apparatus. And so the apparatus is, I add a little scoop, mix it up, make sure I know the masses of everything, and then I'm going to seal this. This is going to be a quick presentation here. Okay, when I heat it up, I want to heat it up where I can control the flame. So what I'll do is I'm going to clamp this onto a ring stand. And the way I'm going to do the clamp is, make sure you clamp it all the way at the top. Otherwise, you're going to be generating toxic fumes. The toxic fumes are when people start to burn the rubber. When they burn the rubber, they make all kinds of toxic chemicals that we don't want to smell. And you can see somebody already burnt the rubber here. It's all bubbled. And maybe today somebody will burn the rubber, but if you start smelling your neighbors' toxic fumes coming from the burning rubber because they clamped it down here or in the middle, tell them to stop. Okay. So we're going to heat this up, but the oxygen is going to be driven off, but we don't want the oxygen to be released into the lab. What we want to do is we want to capture all the oxygen. And the way we're going to capture all the oxygen is by all this tubing and stoppers here. So we're going to put this in here like this. And then we're going to trap it, the oxygen. And how are we going to trap the oxygen? The way we're going to trap the oxygen is like this. We're going to do something called water displacement. And so water displacement, we're going to fill up our flask with water. And then seal it here. So now, as the oxygen is being generated here, I'll just do. You see, it's forcing the water out of this tube out there. But this water, we want to make sure we capture all that water that's coming out of the tube so we know how much water, how many milliliters of water were generated. Because that way we can determine how much oxygen was formed here. And so we're going to capture that in the flask. Okay, so here I'll set up my apparatus. I'll make sure this is full completely with water. And I'm going to seal it here. This is too high. And then what I'm going to do is I'm going to control the heat here. If it starts getting too vigorous, the reaction, then back off. And then start heating it again. And then eventually we want to make sure that it's all reacted completely. So just keep heating it until you see absolutely nothing happening and there's no more gas being generated over here. And then we're going to capture all the water in this beaker here so we know how much water there is. Okay, so let me do that here. Let me capture some water into the beaker here. So let's say I'm generating the O2. Everything has to be well sealed. You don't want any leaks, otherwise you're going to lose. All right. So let's say, hopefully you're going to generate more oxygen than this, but let's say this is the amount, all the oxygen that was generated. Everything's sealed up here. Like so. Uh-huh.
How do you know when you should stop heating and you're not going to generate any more oxygen?
Sometimes it's hard to tell if it stopped reacting, and so what you do is you just keep heating it until you're absolutely sure nothing's changing.
Okay.
That is, there's no more water moving over, and when you look at that, it doesn't look like anything's changed. And then heat it up for a little bit longer just to make absolutely certain nothing happened. All right, now we have to do something here. Do you guys know about equalizing? Like, for example, here, do you see the two water levels are uneven? That means this is like a seesaw. So that means on the right, on your right side, do you see the levels lower? What that means is that on this side, the atmosphere weighs more than the gas. This is like a manometer. I didn't have a chance to talk about the manometer. Now, do you see the two levels are uneven? What's happening is, as I lift this up, it's going to siphon water back into the flask. As it siphons water back into the flask, it compresses the gas. As it compresses the gas pressure is higher and it weighs more. Do you see that the gas trapped inside here is going to be at a higher pressure, weighs more? It's the seesaw. So on your left, it's heavier. Do you see that? So if I drop it down this way, it siphons water the other way. As it tries to siphon water, it creates a vacuum in the flask. And now, which side's heavier? The beaker or the flask? The beaker's heavier, right? So what we want is we want the two sides to weigh the exact same. How do we do that? We siphon water back and forth until the two levels are equal. Do you see now the two levels are equal? Okay. Once you get the two levels equal, we don't want to siphon water back and forth anymore. So what we're going to do is we're going to pinch the hose so water can't siphon back and forth, and then remove it. This is the amount of water that we want. And what we want to do, you know what I just did there? What I just did there is I made the pressure inside the flask the same as atmospheric pressure. So we know what the pressure of the gas inside the flask is. Otherwise, we don't know what the pressure of the gas inside the flask is. Does that make sense?
Yeah.
And so you have to do that equalization step. And now we know how much oxygen we've generated here. This is a little bit more complicated than that, but I'll talk more about this next time. I mean, in class.
If If you just do the whole reaction with the flask and the beaker both on the table, do you have to do that balance?
You have to do that balancing on there because if they're both on the table, it doesn't mean that they're the same level. So if these are both on the table, do you see the levels are mismatched? If they're mismatched, that means that one side's heavier than the other.
Okay.
And so what we have to do is we have to siphon water back and forth until we get it. Actually, it's pretty easy. You just bring it to the same level. That's how much water. Pinch the hose so water can't siphon back and forth, and remove the flask. Does that make sense? Uh-huh.
You do that after you like.
After it's completely reacted, after it's totally done, you do that. I could demo the heating, but I don't want to take too much time talking. Okay, are there any questions with this? So what we're going to do is we're collecting data, the data that we need to collect, and then they say use a pinch clamp. You know, this is not a screw clamp. We have two types of clamps. We have a pinch clamp and a screw clamp. I think you could use a screw clamp, but a screw clamp you have to make sure it's completely pinched. So what I recommend is just pinch the hose like this, you know, and then just remove it. Rather than screwing this, because if you don't screw it tight enough, then some water can siphon back and forth. Unless you want to screw this really tight. Oh, actually, maybe don't. Sorry, don't. The hoses are getting old. Unfortunately. Don't pinch the hose like this. Use the pinch clamp, sorry. Use the pinch clamp even though it's a bit of a pain. Do that. Is this one partners or did it say work with somebody? This one, if you want to work with a partner, it's okay because pinching the hose, you need 3 hands to do that. And so what one person's going to make sure the water levels are equal, and the other one's going to pinch the hose because these hoses I used to be able to pinch close like this, but this one they're so brittle now, they're so old. So all right. There's one other thing we have to do. What else? You have to blow something. What? You have to blow? What I did was I cupped my hand over this and then just blew into my hand. But you don't have to do that. I forgot they have this too. You could use this to blow air. But what do you have to blow? I don't think we have to blow anything.
The gas is generated from the.
Yeah, the gas is going to be generated from that.
It's probably to fill the tube before you start generating gas, so there's no air.
Yeah, well, we're not going to fill the tubes here. There's going to be air there.
Oh yeah, but fill the other tube, the one that should have water.
Oh, yes. Right. We have to do that. Here. Do you see, when we collect the water, what's going to happen is all that water has to fill this first tube here that leaks out into the beaker. Well, you know, that's all air there. And so what we have to do is we have to blow. This is what I was doing earlier. I was blowing this out, right, to fill it. And so to purge the air out of that tube, you can use this.
Are we going to be given that?
Yeah, you'll be given this from the stock room. But just follow the instructions. It should say it there. And then we have to refill this. It looks like you're also going to be given a little weather device. This is going to tell us what the pressure in the room is. The pressure in the room, atmospheric pressure today is 30.06 inches, a little higher than 1 atmosphere. 1 atmosphere is 29.9, I think. It's 19 degrees C, and the relative humidity is 34%. It's sunny. today, so you can see that. All right, if there are no other questions, actually this is a pretty quick lab, so let me, are they saying to do 1 run or 2 runs? Just 1 run? If it's just 1 run, then let me talk about this. Uh-huh. Oh, no, they'll give it to you. I think they're going to give you one of these. We have a barometer there, if you want to read the barometer. And then we have this little digital device. It's 30.06 inches of mercury today. And so what we're doing is we're making sure that the gas trapped in our flask is at 30.06 inches as well. Yeah, you are going to have to convert from inches to millimeters, but I think you can do that. So there's going to be air in our system here. So the way we're going to do this is we need to get the air out of this part here and then fill this with water. And so what you have to do is this. There are a couple of steps I kind of didn't tell you about. One is you have to have water in here to begin with, and then you'll have water in here. And then what we can do is we've got to get water in here completely. And so we need to fill this with water. And so you'll have to figure this out. This is one of those things. Or you can just follow the instructions. And then once you get the water in this hose here, and the water filled in the flask, then you're going to pinch this closed here. Take the hose out and dump out the excess water. And then put this back on here, release the clamp, and then any water that's generated comes from the O2 gas. The O2 gas is going to be generated in the test tube, and it's going to fill this part here. And so initially we're going to have air in here. And as the O2 gas is generated, it's going to force gas out this way here. And so what we're going to do is we're going to generate O2, and then there's air. The air, the amount of air is fixed. And so as we add the O2, any displacement of water will be strictly due to the O2. So we're going to remove the water from here. And so any displacement of water will be captured in the beaker. And what we call this is, we call this an Avogadro's mixture. We're going to use Avogadro's law. I told you didn't have to memorize the laws. But Avogadro's law is one that we want to know. Avogadro's law is that the volume of the gas is directly proportional to the number of moles of gas. And so what we're going to have here initially is the volume of the air in here. And then to this air we're going to add O2. And so the volume of the O2 and the volume of the air are additive. And so this is going to be giving us the volume total. That's Avogadro's. Now, once we have Avogadro's law, I'm going to jump ahead and talk about Dalton's law. Dalton's law says that the pressure of the gas is proportional to the moles of gas. So what we're going to end up with here is this. One more gas in here. Do you know what the one more gas is going to be? The one more gas is going to be water vapor. Because the Maxwell-Boltzmann distribution, not all water molecules have the same energy. There's going to be a small population of water molecules that have enough energy to escape the surface. And so what that's going to do is it's going to generate water vapor, or H2O gas. And so oddly enough, we're going to have the oxygen plus the air plus the water vapor. And so we're going to have three gases in this mixture. Now, how do we handle this? How do I know how much? Well, the water vapor is going to be incorporated into the air and the O2. So what we call this is, we call this the volume of wet air and wet O2. So this is going to be equal to the volume of wet O2 plus the volume of wet air. Here. Where the volume of wet O2 is equal to the volume of dry O2 plus the volume of water vapor. Good. Now things are getting all mixed up, and so it takes some time to sort through this. And so what we need is we need the volume of dry O2. This is what we need to know. But we don't know this. We don't know. We know the volume of wet O2. The volume of wet O2 is equal to the amount of milliliters of water that we captured in the beaker. And so the volume of the wet O2 is what's going to displace the water out of the flask, and we're going to capture that in the beaker, and then we know the volume of that. But where do we get the volume of the water vapor? The volume of the water vapor is a bit more tricky because what we're going to do is, this is an extensive property. The volume of the water vapor, it depends on how much wet O2 I generate. The more wet O2 I generate, the greater the volume of water vapor. However, there's an intensive property that we can measure. And the intensive property is humidity. You know, I said, what was the humidity today? The humidity is 37%. That's intensive, because in the room this big, 37% of this room is
Wet O2.
the humidity. It's 37% of the maximum, and the maximum depends on. This is called relative humidity. You know, if it were 100% humid, it doesn't mean this room is 100% water and we're swimming in a pool. What does it mean? If it's 100% humid, it means that the air is saturated with water vapor, and it'd be very uncomfortable. But the actual amount of water vapor in the air is very small. You know, And why don't they just tell us what the actual amount? The actual amount of water vapor in the air depends on the temperature. Because the temperature is going to dictate how many of the water molecules evaporate here. And so relative humidity depends on the temperature. Well, you know, that's an extensive or intensive? If they say the humidity is 37%, is that extensive or intensive? That's intensive. It doesn't depend on how much we generate. Well, that's how we dictate. When people talk about humidity, they talk about this. Now, what is 100% humidity? 100% humidity we can get from a table. And we call this the vapor pressure of water. This comes from the vapor pressure of water, which is an intensive property. You have a vapor pressure of water table in your lab, correct?
Yes, as we should, yes.
Yeah. So let's take a look. What do you think the temperature is today? Here. 19 degrees C. Tell me what the vapor pressure at 19.0 degrees C is. 16.5 torr. Thanks. At 16.5 torr, then we can figure it out. What's the total pressure today? The total is 30.06. So this is what we can do here. So the first part of the experiment, we use Avogadro's law. For the second part of this experiment, we're going to use Dalton's law. And so with Dalton's law, let's say the volume of wet O2 is going to have a pressure. You know what the pressure of the wet O2 is? It's going to be equal to the air pressure, or atmospheric pressure. And so the volume of the wet O2 is equal to the pressure of the atmosphere. The pressure of the atmosphere is going to equal the pressure of the dry O2 plus the pressure of the water vapor. And so what we want is we want the moles of dry O2. The moles of dry O2 is going to equal the volume of the dry O2 times the pressure of the dry O2 divided by R and the temperature of the dry O2. Okay, the temperature is easy. The temperature of the dry O2 is just equal to the temperature of the wet O2, which is equal to the temperature of the gas or the water. They should all be in thermal equilibrium. We're going to assume they're all in thermal equilibrium. Everything's at the same temperature. Now, the volume of the dry O2 is going to be the same as the volume of the wet O2. They're in the same volume. But the pressure of the dry O2 is equal to the pressure of the wet O2. Actually, let me do this. Which is equal to the atmospheric pressure, let's just say the atmospheric pressure, minus the pressure of the water vapor. So in pictures, this is what we're doing here. In pictures, the first part is this. We'll have some wet air. And it's going to have a volume and a temperature. So we'll have a volume of wet air and a temperature of wet air. and a pressure of wet air. And then to this wet air that's already in the flask, we're going to add some wet O2. And so we'll have some volume of wet O2, and this is going to be the temperature of wet O2 and the pressure of wet O2. Now in Avogadros, this is what we're doing first. In Avogadros, we have to have constant pressure. Volumes are additive. So what we have to do is the air has to initially be at atmospheric pressure, and the wet O2 does. So we have to equilibrate it. We've got to make sure all the pressures are the same. That is, everything's matched. That we have to make sure the water levels are all the same. That everything's matched. And then what's going to happen is we're going to get an O2 and air. So we'll get wet air and wet O2. And the volumes add up here. In the second part, we're using Daltons. When we use Daltons, then what we do is everything's at constant volume. And the pressures are additive. So what we have here is the pressure of wet air is equal to the pressure of wet O2, which is equal to the pressure of the atmosphere. Everything has the same pressure. And then the volume of the wet air plus the volume of the wet O2 is equal to the volume of the mixture. That is wet air and O2. Wet O2. So once we get the wet air and wet O2 mixture, what we do is we separate this into two. So we'll take this container and remove the O2. So we'll have the wet air. Actually, do you want to do that?
Will that put us back to where we started?
What's that?
I said, won't that put us back to where we started?
Yeah.
With 2 containers of wet air and wet O2?
No, it won't. Because where we started was the O2 was added to the air like this.
Yeah.
But here, once we have the mixture like this, then we're going to separate it into 2 containers, and the volume is going to be the same. So the volume of the mixture, let's just call this the mixture. The volume of the mixture is equal to the volume of the wet air, which is equal to the volume of the wet O2. And so the volume of the mixture is equal to the volume of the wet O2 and wet air. Now, the volume of the wet O2, we can split this off like this. We're going to split this off into 2 separate mixtures here. So now we'll have the volume of dry O2 and the volume of water vapor. So here, the volume of wet O2 is going to equal the volume of the dry O2, which is equal to the volume of the water vapor. So what's going to happen here is we're just going to separate this. We're going to have wet O2 and wet O2 is going to consist of oxygen and water vapor. So we're going to put the oxygen in one container and the water vapor in another container. And so now the pressures are not going to be the same. And so we're going to have the pressure of the wet O2 here. and we're going to split it off into two separate containers of equal volume. And so now we're going to have the pressure of the dry O2 and the pressure of the water vapor. And so the pressure of the wet O2 over here is going to result in this. The pressure of the wet O2 is going to result in the combination of dry O2 and water vapor. And so what we're going to do is we're going to get the pressure of the dry O2 using Dalton's law. That is, it's going to be P total minus the water vapor. And so the pressure of the dry O2 is equal to the pressure of the wet O2 minus the pressure of the water vapor. Does that make any sense at all? All right, so we're going to have to do the combination because volume is extensive. We want to represent an intensive. So here, where volume is extensive, we want the volumes to be additive, like this. Here, because of vapor pressure of water, the amount of water vapor changes depending on how big the room is. So we need this represented an intensive, and so this is why we have to do this. And so it's a bit of a hassle, but that's what we're doing with this. Okay, well, I'm going to stop talking here, and you can do this. This is a pretty quick experiment.